Ahoy everybody, Binary Bill here. I'm coming to you from my sailboat Blackjack, along with my first mate, Luna. Today we're going to talk about forces, what a force is, how forces combine, how forces lead to acceleration. We're going to talk about a specific force called lift, and then how lift and other forces relate to sailing. See you out on the water.
Ahoy everybody, it's Binary Bill, and we're out here on the sailing vessel Blackjack with our famous pink shirt crew. And it's a very windy day today, as you can see, and take a look at the sails. These are the sails that are going to drive the boat during our racing sessions.
Okay, let's take a minute to describe what a force is. A force is the interaction between two objects that creates a push or a pull. If you only have one object, you wouldn't have any forces on it. Take, for instance, this ball. If this ball was floating out in far distant outer space without any other objects around it, there would be no forces acting upon it. If we take this ball closer to Earth, then we start to experience the force of gravity. The force of gravity is proportional to the masses of the two interacting objects. The bigger the masses, the larger the force of gravity. If I were to release this ball, the force of gravity will pull it down to the center of the Earth. Now, gravity is an invisible force. We don't see it. And there's also another invisible force, and that is the force of magnetism. So in this plate, I have a bunch of metallic screws. I have my magnet, and as I bring the magnet close to the screws, the invisible magnetic force will pull the screws up to the magnet. And there we see that. Another force that you might experience is the force of friction. When we have the surface of two objects that slide across one another, there's a frictional force that resists the movement of the object. So as I move this roll of tape in this direction, the force of friction goes in the opposite direction, resisting the movement of this roll of tape. One other force that you may be familiar with is buoyancy. So here I have a pitcher of water, and I take a ball and put it in the pitcher of water. As the ball displaces water, the water pushes on the ball with the force of buoyancy. When we describe forces, we use two attributes, strength and direction. Strength describes the magnitude of the force, how much force there is. Direction is the orientation that the force is being applied. In the metric system, we define the magnitude of the force in newtons. In the US imperial system, we use pounds. So if we say that you weigh 100 pounds, it means that gravity is applying a force to your body, pulling you down with the equivalent of 100 pounds of force. The direction of a force can be anywhere in three-dimensional space. It can be up, it can be down, it can be left, it can be right, it can be into the screen, it can be out of the screen. It can be at different combinations at different angles. And there are different coordinate systems that are used to describe the direction of a force depending on how many axes you are evaluating. Now let's do a quick thought experiment. In this diagram, can you tell me which forces are in effect? And can you draw the direction of the resultant forces? Now let's take a moment to talk about what happens when you have more than one force acting on an object. And in that case, the forces will combine. Depending on the direction, the forces will either be additive or subtractive. So suppose you have two forces acting on an object. They're both going in this direction. We might have a 5 Newton force pushing an object in this direction and a 10 Newton force pushing an object in that direction. If that is the case, then the total force on that object would be 15 newtons in this direction. Now what happens when the forces are in opposite directions? We might have a 5 Newton force in this direction and a 10 Newton force in this direction. In this case, they subtract from one another, and the result is a 5 Newton force resulting in this direction. Now in the case where opposite forces are equal, they completely cancel each other out. If we have 5 Newton force moving in this direction and a 5 Newton force moving in this direction, both pushing on the same object, then they will cancel each other out and the net force on the object will be 0. Let's do another thought experiment and take a look at what happens when we're out on a sailboat. In this particular picture, we're just floating around. There's no wind. But there are forces acting on the sailboat. Can you tell me what they are? Can you tell me how they add or subtract from each other? And can you tell me the resultant forces? Unbalanced forces acting on an object will cause it to accelerate or speed up, decelerate or slow down, or change in direction. Take a look at this video of me and Luna playing with a toy. As she pulls on the toy harder than I am, the toy will accelerate in her direction. When I pull the toy harder than Luna's pulling, the toy will move and accelerate in my direction. Notice how the changes in forces applied by myself and Luna change. The direction of the toy changes. It may go up, down, left, right, all because the forces are constantly unbalanced and changing. To help reinforce some of the ideas we discussed about balanced, unbalanced forces and acceleration, I'd like to share this video by famous astrophysicist Neil deGrasse Tyson.
A force is what you think it is, right? You push on something and you create a force that might set it into motion, okay? And if it's something that doesn't move, but it's still fragile, you put enough force on it, you might break it.
Nice, yeah.
Okay? So forces make things happen. And when we say happen, we mean something changes about the object. Typically, it's set into motion. And Isaac Newton first wrote down an equation about this. Okay? He said force equals the mass of the object times the acceleration it'll get if you put that force on that object.
Gotcha.
Okay? So you use that formula. You say, well, here's an object. I'm going to put a certain amount of force, and it has to be like a net force. So in other words, if you put a force exactly opposite mine, then the forces cancel, and then there's no net forces, nothing accelerates.
Right.
So if everything is in balance, you can have very high forces operating, but nothing's going to happen.
Right.
But if there's a slight imbalance, then there will be motion. And so with regard to acceleration, if there's a net force, then the object's motion will continue to increase in speed. You have an acceleration. All right, so there you have it. One last thing, just in detail. If all forces are balanced, it can still be in motion, it just won't be accelerating.
Right.
Okay, so you can have no motion or constant motion. If there's a net force, it will accelerate. That's the point that's going on here. All right. So you're in your car and your foot is on the accelerator pedal and you're sticking to 60 miles an hour, 55 miles an hour. Well, what does it mean if your foot is on the accelerator pedal, but you're not increasing in speed? You're not accelerating. Oh, well, the force the accelerator pedal is trying to put in the car is exactly balanced by the friction of the tires on the road and the air resistance. All of that is balanced. And you're maintaining constant speed. If you want to take it out of balance, you press the pedal even harder to overcome that balance, and now you can pass the car on the right.
Faster. Nice.
By accelerating up to 70, you pass him, and then you slow back down again.
So we know that unbalanced forces will cause an object to accelerate or decelerate or change direction. So let's do a little thought experiment. Take a look at this diagram. I'd like you to match each of the three cases with what will happen to the vehicle, whether it'll slow down, speed up, or something else. I'll give you a second to come up with your answer. Before we start talking more about sailing and sailboats, there are two more concepts that we have to introduce. The first is lift. Lift is the interaction of an object with a curved surface as a liquid or a gas flow over it. For example, let's look at an airplane wing. The bottom of an airplane wing is flat, and the top of the airplane wing is curved. As the air flows over the airplane wing, the air above the wing has to move a further distance and creates a lower pressure. The difference in pressures above and below the wing create a net positive upward force on the wing, trying to lift the plane upward. The shape of a sail on a sailboat is very similar to that of an aircraft wing. As the air flows across the sail, it pushes it into a curved shape. On the outer edge of the sail, the wind or air has to travel a longer distance, creating lower pressure than on the inside of the sail. This creates a net lift force. The net lift force is perpendicular to the edge of the sail, and therefore not all of that force is in the direction that moves the boat forward. This brings us to the next concept, decomposition of forces. We can divide that lift force into two different components. One portion of the force is pushing the boat or the sail forward, and then the second component of the force is perpendicular to the direction that the boat is traveling and is creating a sideward force. This forward force is what pushes the boat forward and accelerates it through the water. Let's watch the following video for more detail on all the forces that interact on a sailboat and how that helps the sailboat move forward through the water.
The following KQED production was produced in high definition.
Today's sailboats apply very different principles to harness the power of wind and wave. So if you want to master modern sailboats, you'd better learn some physics.
So why did the wind shift? Just because?
The Quest team attempted to do just that on a recent sailing lesson at Modern Sailing Academy in Sausalito, California.
I think students, when they first come here, they know that the wind will push the boat because they see like a plastic bag being pushed across the street. So they can understand right away that the boat can be pushed, but what they have to learn is the boat can also go into the wind by using aerodynamics. Just like an airplane wing, the sail can lift the boat into the wind. So that allows us to go almost any direction we want to go except for directly into the wind. Okay, hang on now, go straight. Go straight for just a second. You gotta get the boat speed back up. Just go straight for a second.
So modern sailing's not all about being pushed by the wind. Something is happening at the sail that makes it fly like a wing. And that elusive something is a force called lift. To help us understand what lift is, we've brought in some heavy hitters from NASA Ames Research Center who just happen to be avid sailors.
We call it lift because of the analogy to an airplane wing, I think. Well, now in a sailboat, that's all turned up on end, right? So now what we think of as lift is really, in our normal frame of reference, is a side force.
I think a lot of people don't realize that they are exactly an airplane wing just stood up on its side. And granted, it's a floppy airplane wing, but it works the same. When you want to get geeky about it, you can really start looking down at the nitty-gritty and really start learning a lot about how the sail works. What I'm about to do is start introducing some glow-in-the-dark dye into the water. You notice that the streamlines on the lower side of the image are curving around the outside of the airfoil shape. Since those streamlines are curving, it has to accelerate a little bit. When it accelerates, it creates a lower pressure, and that's what actually generates the lift. And that lower pressure on the downside of the sail sucks the sail downwards to the bottom of the screen.
Essentially have high pressure on one side, and that higher pressure is trying to move toward the low pressure side and putting a pressure on.
So as the wind travels along a sail, the sailboat's being lifted, or actually sucked, towards the curve of the sail, mostly to the side and slightly forward. But the wind generally hits the boat from the side, so why doesn't it just slip sideways? Because sailboats have wings above and below the water.
A sailboat, like anything dynamical, exists in sort of a balance of forces. The sail's above the water acting as a wing, and the majority of the lift that they're producing is in a sideways direction to the boat. Only a small component of that lift force is actually angled forward. Now, under the water, there's a keel, and as you move through the water, it's also developing lift. Its lift is predominantly sideways also.
In a modern sailboat, the keel and sail work together to move the boat forward. It's kind of like squeezing a watermelon seed between your fingers. Your fingers put equal sideways pressure on both sides, but the seed still shoots out in a forward direction. In a sailboat, the sail and keel's sideways forces cancel each other out, leaving only the forward force. That squeezes the boat forward, and bam, we're sailing.
Let's take a few minutes to review and answer some questions. What are the forces acting on a sailboat? I'll give you a couple of seconds to think about that. The primary forces working on a sailboat are gravity, which pull the boat down towards the center of the earth, buoyancy, which pushes the sailboat up against gravity. You have the lift caused by the sails and the wind bending around the sails. And finally, you have friction caused by the boat moving through the water and the water resisting the movement of the boat. The next question is, what causes the sailboat to move? I'll wait a couple of minutes for you to think about that. A sailboat will accelerate forward due to the forward lift force produced by the sails. In the opposite direction, friction resists the forward movement of the sailboat. When we get to a point that the forward lift and the aftward friction force are equal, the boat is in equilibrium and will continue at a constant speed. The next question is, how do sailboats work without the force of the wind? I'll give you a moment to think about that. So without wind, there's no way for the sails to create a lift force to move the boat. The boat would just float on the water and stay in one place. Does anybody know why you can't sail directly into the wind? I'll give you a moment to think about it.
What happens when we sail directly into the wind? Sails just flutter and luff, giving us no lift or no force, so we can't move. Now, if we turn off the wind a little bit, you can see the sails starting to take shape, and they are starting to create a lift force that is driving the boat forward. And This is the closest that we can sail to the wind without the sails stalling and still having a force that pushes the boat forward.
In order for the sails to generate a lift force, they must maintain a proper curved shape. If you're sailing directly into the wind, the sails will just luff and not be able to create the lift force. If you want to sail directly into the wind, or in the direction into the wind, you need to sail a zigzag course called tacking, each at 45-degree angles to the wind as you work your way up the ladder to your destination. Well, that's it for this video. I hope you have a greater appreciation for sailing and all the forces that are involved in making a sailboat move. Hats off to everybody, and hope to see you on the water.